Then we'll pick up where we had ourselves the last time. So we kind of talked about what intermolecular attractions were. Now we'll go through the four major ones, listed from weakest going into the strongest. So the very weakest are called London's dispersive forces. I just call them London's. Sometimes they're mistakenly called van der Waals, but van der Waals really refers to all of these intermolecular attractions. But anyway, this happens when two molecules collide with one another, and they deform each other's electron clouds. So here I have two symmetrical, maybe even non-polar particles. They're going to smash into each other. I had one completely win. It didn't get deformed. And the other one has its electron cloud totally deformed. So the electron cloud, because of this collision, is not symmetrical. It forms a dipole. You take negative charge and you push it over here. So this partial positive over here is because this is closer to the nucleus over here, and it's going to be attracted to the negative charge of this electron cloud over here. So I mean, this is very simplistic. In fact, what you would expect is that neither one would win. The electron clouds just bounce back and forth during the collision, which is a form of magnetic field oscillation. And anyway, during that collision, they're attracted to each other because of these induced dipoles that weren't there before. And then they bounce apart without losing any energy, because electrons never bang into other electrons. Electrons don't pass through anything except for a total vacuum. So electrons do not experience friction. So these things smash into each other, and for a fraction of a second, they're attracted to each other. And then they bounce apart just like nothing happened. But they're extremely weak, and the reason why they're important, because if you are a non-polar molecule, this is the only attractive force you will ever experience. And so, just to show you how important it can be, this I took from organic chemistry textbooks. So here's two organic molecules, completely non-polar. This one is spherical, this one is linear. So the boiling point for the neopentane, this one is 9.5, this one is 36. That's a huge difference in boiling point when they have the same molar mass and everything else. So the explanation is more spherical molecules don't have very much what we call van der Waals contact surface when they collide. If you take the linear ones, they can have much larger contact surfaces. So you can imagine that you have these two things like this, and they're right up against each other, and because they're not at 0 degrees Kelvin, they're vibrating. And as they vibrate in place, they're deforming each other's electron clouds, and you have an attractive force across this whole surface area. Whereas spheres would be more just like this, right? Here's a practical example of that. What is the difference between a fat and an oil? Well, at room temperature, a fat is a solid and oil is a liquid. And so if you look at the structure of the fatty acids that make up a fat molecule, like this is glycerol right here, these are carboxylic acids called fatty acids. These are straight chain right here, okay? And so to kind of show you what that means, if I can do that. There's something that will work. So I take these tetrahedral atoms right there, and if I put them like this, that gives you what they're trying to draw there. You see that? So these things basically mimic this. So fat molecules, mostly nonpolar, so the major attractive force is going to be London's, but they're linear and they're basically straight chain. Now, if you've heard of unsaturated fats, what they're really talking about is the fatty acids that make up an oil. So again, here's glycerol, same thing over here. Here's the ester linkage between the carboxylic acid and the alcohol of glycerol. And notice that you have the same squiggly line right there, but look at these double bonds right there. Those are unsaturated. And in nature, double bonds are almost always cis. Okay. Anyway, so here's a double bond in a long chain right here. And you see this? If I look at this carbon, there's a small one here and a big one here. If I look at the other carbon that's in the double bond, there's a small one here and a big one here, which would include this whole thing. This is trans. Trans fatty acids you may have heard about are not good for you. They weaken the immune system, supposedly. But if you look at this, it basically has that same squiggly shape, doesn't it? But look what happens if I make it cis. If I make it cis, you can see the squiggly bond goes like this, then all of a sudden it makes a big turn. This is a 120-degree turn right here. And that's what you're seeing right here. That's a cis double bond, cis double bond, cis double bond. And so that causes the chains to kink out a little bit and it gets more spherical. And so the molecules that make up oil are more spherical than they are linear. Anyway, so the next one are dipolar attractions, also known as Keesum, but very rarely. And so these are with polar molecules. So London's was with anything that collides with one another, right? But if you're a nonpolar molecule, that's the only attractive force you'll ever experience. But if you're a polar molecule, you'll be attracted to another polar molecule. So here's hydrogen chloride. The difference in electronegativity is 0.96, which makes it a polar covalent bond, so therefore you assign charges. So here would be repulsion, and here would be attraction. But we know that attractive forces are more important than repulsive forces. We talked about that yesterday. So polar molecules are attracted to other polar molecules by dipole to dipole attractions. Then, what the heck is a hydrogen bond? So if I could be king of chemistry for a day, that would be one of the first things I would change. It is not a bond, it is simply another attractive force. What it really is a slightly stronger dipolar attraction. So the difference is that you have one molecule has a large partial positive and the other one has a large partial negative. So how do you get that? So we take the three most electronegative elements on the periodic table, and hopefully you'll never forget this because it spells fun. You know, the Chinese version, right? Like Chow Fun. And then you bond it to a hydrogen atom. So it's a polar covalent bond, but because these are so electronegative, they strongly pull the electron away from hydrogen, leaving this to be a large partial positive charge. And hydrogen is unique because it has only one valence electron. And when you start to pull that one valence electron away, there's nothing there to shield the proton that's in the nucleus. Any other element If you start pulling that one valence electron away, there's going to be core electrons underneath there to help shield the nucleus. So this is why it gets the word hydrogen bond. So how do you get the large partial negative charge? You just simply have to have a polar molecule, and it has to have an F, an O, or an N. So in other words, both molecules have to have some form of fun. So here's a hydrogen bond in water. Here's the O with its partial positive. What does the other molecule have to have? An FH, an OH, or an NH. Oh, here's that OH, so that is a hydrogen bond. It meets the criteria. So water molecules are attracted to each other by Londons, by dipolar attractions, and by hydrogen bonds. Then if you really were to listen to my words carefully and go confirm things on the periodic table, what you would find is that, oh, chlorine actually has a higher electronegativity than nitrogen. Oh, Harry's lying to you. Well, electronegativity is good for a lot of things, but it can't explain everything. So here's what I mean. If we look at fluorine, fluorine is in period 2. Here's fluorine. So that means, it's not working out too well, is it? That means that fluorine has its valence electrons in shell number 2. If you go to chlorine, it has its valence electrons in shell number 3, which is a much larger shell containing a lot more electrons. So I just give this rough estimation right here. If you had a negative charge on fluorine and chlorine, both of these are full negative charges, right? But what would have the greater charge density? This is really what's important for attractive forces, is the charge density. How intense is the charge? So on the fluoride is going to be way more intense because the surface area is just greatly reduced compared to chlorine. So here's some examples. We talked about this a little bit before. So ice has 4 hydrogen bonds. That's why these hydrogen bonds align right here at low temperatures, leaving that void right there, which is why the density of ice is less than the density of water. Let's see. We talked about all of that. You can imagine what the world would be like if water behaved like most substances, where the solid is more dense than the liquid. Then you go to a lake or maybe even the ocean, and if you did form ice, it would just sink to the bottom. Now it's far away from radiation from the sun, and it's going to stay that way. Lakes would be frozen solid all the time. Maybe even the ocean would be solid, who knows? And then I thought I would give you an idea of how important attractive forces are. This is dichlorofluoromethane. So dichloro, fluoro, and if all these were hydrogen, it would be called methane. So this is known as R22, or refrigerant 22. And let's just look at the attractive forces that are possible with this refrigerant. This could do hydrogen bonding. This could do dipole attractions. This could only do London's attractions, right? Because it's nonpolar. But what if you had 2 of these molecules over here? Say, for example, can it do hydrogen bonding? Here's the F of 1 in one molecule. What do I need in the other molecule? An FH, an OH, or an NH? and it wouldn't be there. So the strongest attractive force between two molecules of R22 is dipolar attractions. So let's think about how an air conditioning has to work. There's two sides of the air conditioner. One is the compressor. So you take the gas and you compress its volume, and the temperature of the gas when you compress it goes up. So what you do is you blow air across that to push the heat out of the room. Then that liquefied R22 comes into the other part of the compressor where it's allowed to expand. And when gases expand, they absorb heat energy. It gets cold. Then you blow the cold air across that into the room. So can you imagine if some water got into that? Say your R22 was contaminated with water. What would be happening with this fluorine right here? You'd be having hydrogen bonding. And I don't think your air conditioner would work anymore. I have a friend with a air conditioning business, and I always give him a hard time. So you're installing an air conditioner and it always tells you which direction to point it. It's kind of funny. You know you got to point it the wrong way when the hot air is going into the room. So R22 is replaced by 134A. Why? Because the ozone depletion potential goes down to about 0. Global warming potential is lowered. Even though the lifetime is lowered, it's still a benefit. And if you look at this number right here, 1300, what does that mean? That means it's 1300 times more powerful than carbon dioxide. So yeah, we got to take care of this stuff. We can't let this go into the atmosphere. It's just devastating. Besides destroying the ozone. So then the last one we'll look at is called ion to dipole attractions. And anyway, I don't have numbers on this, but they're stronger than hydrogen bonds because you have a full charge over here. So there's no way to really line something up on a particular atom. It's that this whole thing has a net charge of -3 that's going to be attracting the partial positive of the water molecule. But here's a way to think about it. To melt sodium chloride takes 801 degrees Celsius. That's pretty hot. That means that the attractive forces between sodium and chloride are strong. Well, that's the ionic bond. But yet, I can take sodium chloride and put it into the coldest water and it simply dissolves instantaneously. And here's the reason why. The sodium ion becomes surrounded by a layer of water molecules called the hydration sphere. And you can see the partial negatives are pointing towards the full positive charge over here. But what you have on the surface of the sphere is all the partial positives from the the hydrogen part, right? But what you've really done is taken this small sphere with a positive charge on it and put it onto a much bigger sphere with a positive charge on it, which increases the charge density dramatically. But then that's simply the first layer of hydration. There's going to be a second layer and a third layer. Here's the partial positive. It's going to attract the partial negative of another water molecule. Then what happens to the chloride ion? It's a similar thing, but this is attracting the opposite side of the water molecule. So then here's the first layer, and then the second layer, and the third layer. By the time you know it, these two things are not even very attracted to each other anymore. And here's an explanation for why sodium chloride dissolves in water. It's because the net attractive forces between water and the sodium and between water and the chloride, those attractive forces are greater than between the sodium and the chloride. That's the reason why it dissolves. Anyway. So questions so far? So just to review how to determine if a molecule is polar, how to draw attractive forces. So you draw the Lewis structure for one, and if it has polar bonds, you have to put the charges on there, right? And so say here's ammonia, okay? So I got the partial charges on here, and then when I try to draw the hydrogen fluoride, that partial negative is going to attract the partial positive of the hydrogen fluoride. Now, what is the type of interaction between ammonia and hydrogen fluoride? Well, it's going to be London's. It's also going to be dipole to dipole, and doesn't meet the criteria for being a hydrogen bond. Here's the FH in one. What do I need in the other one? An F, an O, or an N, and there's the N. Here's another way to draw it. So do you think hydrogen fluoride would dissolve in ammonia? Yes, they would, because they're attracted to each other by hydrogen bonds. What about between acetone and water? So does acetone dissolve in water and vice versa? Well, here's the structure for acetone. Notice that there's only one polar bond in there, right? So that's going to be an attractive force with water. That's going to be an attractive force with water. So here's the OH of one. What do I need in the other one? An F, an O, or an N. Then here's a C. That's a carbon. So it's going to attract the partial negative of a water molecule, which would be the non-violent electron pair. So here's the O of one, but do I have a FH, OH, or NH over there? No. So it doesn't meet the criteria for being a hydrogen bond. It's simply dipolar. So that means that water and acetone will dissolve in one another. What about acetone and acetone? Notice that there's dipolar, but not hydrogen bonding. So wait a minute. There's stronger attractive forces between acetone in water than acetone to acetone. Yes, that's correct. Why does acetone evaporate so quickly? Because acetone is fingernail polish remover. We know it evaporates extremely quickly, right? It doesn't have hydrogen bonds, it simply has dipolar attractions. But yet, it remains a liquid in the bottle. So here's another one, acetone and acetaldehyde, also known as ethanol. Here's with acetone and acetic acid. So hope you get the point. And here's some other practice over here. So here's the HF, here's the O, right? So that's the hydrogen bond. And then this is nonpolar. The sulfur to hydrogen is only 0.48, so it's nonpolar. But hydrogen sulfide is a gas at room temperature where water is a liquid, even though the mass of this is twice as much as water. Attractive forces are more important than the masses. Here's a polar molecule, here's a nonpolar molecule. The strongest attraction possible is London's. They're not going to be attracted to each other unless they actually bang into each other. So here's an ion in a dipole. Here's an ion in a nonpolar molecule. This is simply London's. So back to the acetone again. So acetone has dipolar attractions. Acetone forms hydrogen bonds with water. So if I were to squirt some acetone on the table and right next to it some water on the table, the acetone would evaporate much more quickly, right? Because of weaker attractive forces, even though it's heavier. And if I took those two puddles and I smashed them together, mixed them up with my finger, they would dissolve into each other, wouldn't they? Because they're attracted to each other by hydrogen bonds. And then that mixture would evaporate more slowly than acetone, but faster than water alone. And then here's an ion. Here's another ion. I'm not trying to trick you. I'm just trying to point out that this is not an intermolecular attraction. This is an intramolecular attraction. That's an ionic bond. And attractive forces partially explain the solubility. Attractive forces partially explain the physical state of matter. And the physical state of matter really depends upon at least four things. The nature of the substance, I put as first. Then went into kinetic theory. This is kinetic theory right here. If I have a high temperature, then there's a high kinetic energy, which means that there's a high velocity, right? So the faster you're going, the more likely you're going to be able to break away from intermolecular attractive forces. And notice that molar mass is in there as well. So at the same kinetic energy, if you have a big mass, the velocity is going to be small. If you have a small mass, then the velocity is going to be large. And then we can look at some molecules that are all nonpolar from fossil fuels. Methane is a gas, only attracted to each other by London's forces. Gasoline is a liquid that evaporates quickly. All London's forces, simply the mass effect, right? The mass is bigger, so it's harder to get it into the vapor phase. Oil is a liquid that does not readily evaporate. The oil in your engine is around C20, much heavier. But can the oil evaporate out of your car engine? Yes, it can if it overheats. And then tar, bitumen, pitch, these are solids that contain very high molecular weight hydrocarbons. We mix some gravel with it when it's hot, let it cool down, and we call that the road. So you drive on this, you cool your engine with that, you burn that, and you might even burn that. Of course, pressure, very important for gases because of PV equals nRT. So I just really like this cartoon. It's just so dumb, I had to use it. And see, he's dissolving because he's a polar bear. Chemical attractions, human attractions, and no attractions. I don't know, terrible. So any questions on that chapter at all?
No, it makes sense.
Okay, good. So then, chapter 16 chapter 16, what I'm trying to get at over here, since you're supposed to know all this stuff here, it's the end. Oh yeah, the effect of having strong attractive forces. So if you have strong attractive forces, you're going to have a high melting point. You're going to have a high boiling point. So here, for the general chemistry type students, I had to explain the difference between boiling and evaporation. In both cases, you're going from the liquid into the gaseous phase. Evaporation can occur at any time, or I should say any temperature, where the boiling point is more specific in that you start to see these bubbles forming within the body of the liquid. They rise to the top, and then we say, oh, it's boiling. And if I'm boiling water, what's evaporating from here? Water. And what's going from the liquid to the gaseous state inside here? In other words, what's inside that bubble? Water. Please don't tell me air. So here's water, ethanol, and acetone. Okay. So hydrogen bonding, less hydrogen bonding, only dipolar attractions. Look at the boiling points, right? So then I talked about distillation a little bit and things like that. So if I have a mixture of water and ethanol and I start to evaporate it, maybe not necessarily boil it, but evaporate it, I'm going to be measuring preferentially ethanol up here because it has a lower vapor point. So then it comes over here, gets cold and condenses, right? After all the ethanol is out, I'll start to read 100 degrees over here because then I'll just be recondensing the water. And then if you have strong attractive forces, it's going to be harder to go into the vapor phase, so therefore you're going to have a lower equilibrium pressure, equilibrium vapor pressure. So this is probably kind of unique over here, so I should explain that. So here's the temperature where you go from a liquid to a gas. Here's the average temperature over here, the average kinetic energy for molecules. Notice that only a small amount of them are able to go into the gaseous phase. And which are the ones that are going into the gaseous phase? The ones that have the most kinetic energy. Then at T2, I can see most of them are able to go directly into the gaseous phase, so that's probably boiling. But why we sweat is to cool ourselves down. So if you look at the distribution over here, which ones are able to get into the gaseous state? Only the ones with the most kinetic energy. So you're essentially removing kinetic energy from the surface of your skin. And we could even use that to explain freeze drying. Freeze drying, you don't even need a freezer. All you need is a vacuum pump. So when you first put, say, a glass of water in over here, you might see some boiling. Those are very high energy molecules because remember it's a distribution, okay? But mostly you won't if you do it correctly. So you start getting evaporation over here, and then you're sucking out all those water molecules as they go into the vapor phase. So what you're really doing is removing the kinetic energy. So the water gets cold, and then it starts to freeze, and then you're going from the solid to the vapor phase, which is sublimation. But you don't need a freezer, you just need a vacuum pump. Then if you have strong attractive forces, you're going to have a high surface tension. So if you look at, say, a water molecule within the liquid, it's being pulled in every single imaginable direction because of all the attractive forces to other water molecules. But if you look at right on the surface, there is no water molecules right here. These are non-polar molecules. Those are air particles. So this is a weak attractive force. So essentially what happens is that its magnetic fields become stronger in this direction, and it forms essentially a skin. So here's a bug taking advantage of that. Here's where you have high surface tension, cold, still water. You go out to the ocean, and what's the difference? All that surface tension has been reduced because of all the kinetic energy that's in the ocean. And then if you have strong attractive forces, all of these types of values right here are going to be high. Heat of fusion, heat of vaporization, specific heats, are all going to be high. And I compared water to acetone, and you can see it's quite a difference. It's all about attractive forces. So here's some type of questions you can answer. Water boils at 100 degrees. Ethanol boils at 78.5 degrees. Which should have the highest surface tension? And you might be thinking before this lecture, oh, they're not related. But yeah, the relationship is attractive forces. So I'm looking at water has much stronger attractive forces than ethanol. The strong attractive forces means that water should have a higher surface tension. So if you read through these things, it should make perfect sense to you. Yeah. I just had to find a use for that picture when I saw that. And some of my favorite cartoons. I just love this one. It's called Irony. So my wife is a vice principal at a middle school, and so I give her and her colleagues over there a hard time. You come up with stuff like this, and they're just like, oh, yeah, okay, cool. So I was there the other day, and I was trying to find ways so they could incarcerate any kids that came down with the COVID virus. Lock them up in the air conditioning thing. Okay, so pretty much that is the review. So we went over the syllabus. We reviewed parts of 3 chapters that I thought were important. And they're important because when we look at organic functional groups, what we're really looking at is like naming is one important thing. And then the chemical reactions that they do is another important thing. And then finally, the physical properties. Well, by doing this review, we just covered all the physical properties. You'll see what I mean when we get to it. So first, let's look at this chapter. So this is the first chapter that has to do with organic chemistry. So alkanes, alkenes. So these are all single bonds. This has one or more double bonds, one or more triple bonds. A halide is anything from group 7 on the periodic table, right? Like methyl chloride, and aromatics like benzene. And so There are some generalities we can make between organic compounds versus inorganic compounds. Not really good. I mean, you can't really, they're not the greatest way of describing things. So you can find inorganic compounds that say are combustible, but most of them are not. And most of these are. Okay. So where do we get organic compounds from that we use in everyday organic chemistry? Well, from crude oil. So by the way, the early Earth did not have high mountains and deep oceans. That came from plate tectonics. So there was lots of shallow estuaries and swamps. It was really swampy. And as plate tectonics started to happen, it was pushing organic material under the ground. And several million years later, you take this organic material, it's been at high temperature and high pressure for millions of years. Every reaction that's going to happen has already happened. So we dig it up, and just about the only thing it will do is burn, go back to forming carbon dioxide. But if you listen carefully enough to that description, that's a one-time gift. Fossil fuel was a one-time gift. You're not making fossil fuels of any significance right now because plate tectonics has already happened. So anyway, all of that biomass was created from carbon dioxide. So the plants absorb carbon dioxide, made oxygen so we can have animals. So you removed all that carbon dioxide from the air. So the atmosphere of Earth cooled down because there's less global warming. Now, the humans have gotten really, really smart, and they go and they dig up all that fossil fuels, and what do they do with it? They burn it and put it back into the atmosphere. And then they wonder what's happening. What's going wrong here? So here's just a crude way to show you how we fractionate different grades. So tar is between 25 and 50 carbons all bonded together with appropriate number of hydrogens. And if I heat this up, some of the stuff will vaporize over here, and then some of it keeps going up, but some of it starts to condense right here. So this drains off over here. Tar remains down here. Fuel oil, what we burn for fuel, is very thick. And then if it goes up higher before it condenses, that might be motor oil. Even higher would be diesel. Then higher than that would be jet fuel. And then finally gasoline. And then anything that doesn't get condensed is natural gas between methane and butane. And I get really irritated when I look out at Campbell Industrial Park at night and I see them burning off all this natural gas. It's like it's cheaper for them to burn it and get rid of it because they're just really busy making money off of this. It's all about making money. So first we'll look at the hydrocarbons, only hydrogen and carbon. And so how do we name them? So we do naming, physical properties, and then chemical properties. And every chemical property, I'll give a number. I'm going to give a consecutive number. So it goes by the number of carbons. So one carbon in a row is called methane. And if I take off one of the hydrogens, it becomes the methyl group. That's important because if I have a long continuous chain and I add this to it, then I call that the methyl group. It's called an alkyl group. So then ethane would be ethyl, propane would be propyl, Butane would be butyl. Pentane would be pentyl. See, hexane is 6 in a row, right? Hexyl. And 7, 8, 9, 10. So you should at least know the first 10. And then the system keeps going. So undecane, dodecane, tridecane. But you should know at least the first 10. And then there's some variations in this. So first we'll go through some of the terminology that they use or used to use and sometimes still do. N meant normal or straight chain. We don't use that anymore. But like, for example, this would be called, say, N-butane because it's all in a row. That'd be called N-butyl because it's all in a row. Then iso means that it's split on the end like a fishtail. So look, there's 3 in a row, so it's propyl. It's fishtailed, it's split, so it's called iso, isopropyl. This would be called isobutyl. Okay. Could you see that we could have actually called an isododecyl? It is a system, but it's kind of a confusing system. So what about when you get to butane? Now there's more possibilities. So with isopropyl, there's simply N-propyl and isopropyl. That's all there is. But if you get to 4 in a row, 4 total, I should say, then you have split on the end, which would be isobutyl. This is called sec-butyl. The reason it's called sec-butyl is because that carbon in blue right there is a secondary carbon, meaning that it's bonded to 1, 2 other carbons. And that's confusing because if it bonds to another carbon, it would then become a tertiary carbon. And if you look at tert-butyl, which stands for tertiary, that carbon, before this whole thing bonds to something else, that carbon right there is bonded to 1, 2, 3 other carbons. When it bonds to another carbon, then it becomes quaternary. Here's just a quick way to see how naming works. So the IUPAC name for this right here is called 1-propanol. Well, here is propane, right? The root is propane. But if I take 1 hydrogen off, it becomes propyl. But it's still got 1 more place to bond, doesn't it? So if I put a hydrogen on there, it becomes propane. If I put an alcohol on there, it becomes an alcohol. So now this would be called 1-propanol. It's its IUPAC name. That's the International Union for Pure and Applied Chemistry. So here I put it on carbon number 1. That'd be called 1-propanol. If I would have put it over here, it'd be called 2-propanol. If I would have put it over here, it would be called 1-propanol again. So if I take this chain right here and I rearrange it by moving this over here, then this becomes isopropyl and then an alcohol, or 1,2-propyl and all for alcohol. So this right here is this. So if I take this and put a hydrogen right here, it's simply propane. If I put an alcohol right here, it's 2-propanol, or isopropyl alcohol is the old-fashioned name. See how that works? I mean, we're going to see a lot more of this, but I just wanted to get you with the general idea. So what I put in parentheses over here was a way that they tried, and I don't know what they're doing with it now, whether it's simply abandoned or not. But when I first took organic chemistry, it would be in, I guess, the late 70s. You had to memorize a whole bunch of these. There was no prisoners taken. So then somebody came along and said, well, that's so complicated for the poor students. So they tried to come up with another way of doing it. So isopropyl would be called methyl ethyl. So here's the ethyl, and on it is a methyl. Here's the propyl, and on it in the number 2 position is the methyl. But they pretty much abandoned it, so yeah, we'll see. So if you look at these 2 molecules right here, they're the same kind of molecule, the same molar mass, they would have the same chemical formula, but they have different structures. So we have to know the exact bonding structure to know how to name it and what the molecule is. So these are called structural isomers or constitutional isomers. If I have that same formula right here, C2H6O, that could either code for diethyl ether or ethanol. Totally different molecules, right? And later on, we're going to look at stereoisomers. And I'll see if I can throw something together real quick on that. Probably can't be quick. This probably won't be quick. Sorry, I'm being as quick as I can. Okay, like that. So. Okay, so here's 2 molecules, and these 2 molecules are the same in that they have the same atoms bonded to the central carbon. So they have the same chemical formula. But I'm going to try to line all these up. Okay, this one works. So you see when I superimpose them like this, the different colors are all together, right? That's the same molecule. But what happens if I switch any 2 around? Now when I try to superimpose them, oh my God, I got red and red, green and green, but look, the other ones are not there anymore. So these are different molecules. The bonding arrangement is exactly the same, but they're different molecules because of their shapes. And it turns out they're mirror images of one another. Oops, how am I doing that? Okay, those are mirror images of each other, and they're called enantiomers. And that's what we mean by stereoisomers. Okay. So we say that they have handedness. Like a pair of sewn gloves, one goes for the right hand, one goes in the left hand, and they're not reversible, right? If you take your hand and put it up to the mirror, what do you see? The mirror image, but you can't make them superimpose, so they're the same, but they're not the same. You have different stereo properties. But that's the last chapter in this unit. So The hydrocarbons only contain hydrogen and carbon. So we'll look at what's called the aliphatic hydrocarbons. That means there's no aromatic rings. That would be alkanes, alkenes, and the cyclic ones, and alkynes with the triple bonds. And then finally, the aromatic ones that have aromatic rings, such as benzene. Okay. So here is the definition of R. Sometimes we use R to designate certain parts of a molecule to make it simpler to write. So let's go into the naming of these. So the root name is the longest continuous chain. Then once you identify that, you identify the substituents that go on to that longest continuous chain. The substituents are named by the total number of carbons and not the longest continuous chain. But the root name is the longest continuous chain. The substituents is the total number of carbons. Then we give prefixes for the amount of each substituent. We don't use mono. And then we find the lowest numbering system. And then we put the substituents in alphabetical order, not using the prefix. And then we put commas between numbers, dashes between a number and a letter. So for example, look at this molecule right here. I have to find the longest continuous chain. Is it 1, 2, 3? Is it 1, 2, 3, 4? Or is it 1, 2, 3, 4, 5? Notice it could be 1, 2, 3, 4, 5 that way as well. So we know that this continuous chain is 5 in a row, so the root name is going to be pentane. So a little bit of an explanation. I'm very dyslexic. And I don't know how I ever got through organic chemistry. And then it was like some cruel plan of God that turned me into an organic chemistry teacher. But I found ways over the years to compensate. So if I have this on a piece of paper, I will take a pencil and draw through the longest continuous chain so I don't get confused. Here I did it in blue, right? Now what's added on to that? What are the substituents? This is a substituent, it's a methyl. This is a substituent, it's another methyl. Okay, so now how do I get the name 2,3-dimethylpentane? Pentane is the longest continuous chain. It's dimethyl because there's 2 methyl groups. And where are they? What numbered carbons are they at? Here's your choices. 1, 2, 3. So if I start from here, it's 2, 3. If I start from here, it's 1, 2, 3, and 4. So this way it would give me 3 and 4. This way it gives me 2 and 3. So the name is 2, 3 because that's the lowest numbering system. So here's another one. So hopefully you go through this and you really understand how it works. Then I took this and I drew something similar to it. And I'm going to ask you, are those 2 molecules the same or are they different? You would have to like literally put your finger on here and put your finger on here and go carbon to carbon to figure that out. But the easiest way to figure that out is just to give names. So look, here's this name, right? Longest continuous chain would be 1, 2, 3, 4, 5, 6, 7, 8, or 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 is the longest continuous chain. And what do I have on there? There's 3 methyl groups, right? So it's trimethyl. This would be an N-propyl or just propyl. And what would be the numbering system? 1, 2, 3, 3, 4, 5, 6. So that'd be 6 propyl. If I came this way, then it would be 1, 2, 3, 4. It's much higher numbers, right? You end up getting the same name. So I know that they're the same structure. So here's some full structures. Okay. Here's a full structure. And then we have what we call condensed structures. So notice that with a cyclic compound, we often just leave out the hydrogens, right? And we combine this into CH3, so that means that that carbon has 3 hydrogens on it. This carbon has 2 others that are missing. And then this becomes a CH3, that becomes a CH3, and both of these are bonded to that carbon, which is a CH. And then look what we did here. This is called a methylene group. There's 3 of them in a row. So I made the methylene group, and there's 3 of them. And at the end, it's not a methylene, it's a methyl group, right? So it's a CH3. And then we do skeletal structures sometimes, where every corner or end is a carbon atom. Okay. See how that works? So it does take some time to get used to that stuff. And over the years, I watched students, and some of them are really good with this, and others are not. They have to keep doing this all the time. But anyway. So questions so far? I can't see the, for some reason the chat doesn't show up when I'm sharing screen. Okay. So let's name some cyclic alkanes. So we use the word or the prefix cyclo, and notice that hexane and cyclohexane, see, they don't have the same formula, do they? They're not isomers. So when you're going and using a numbering system, you either go clockwise or counterclockwise. You cannot do both. You go the way that gives you the lowest numbering system. And then we'll see that we're going to end up with what's called geometric isomers. So these are a type of stereoisomer. They have the same molecular formula, same structural formula, but they have different shapes. So cis means the substituents are on the same side. Trans means that the substituents are on the opposite sides. So let's just go through these names. So I got 1, 2, 3, 4, 5 carbons in a row. So that would be pentane. But it's cyclic, so I say cyclopentane. So this ring is cyclopentane. And then here's a methyl and a methyl. So it's dimethyl. And where are they on the ring? 1, 2, or 1, 2. So it's 1, 2 dimethyl cyclopentane. Then, see those wedges are both going the same direction? That means that they're on the same side, so therefore they're cis to each other. Same side. If I were to take this and flip it upside down, it would look like this. Here the methyl groups are coming towards your face. Here they're going away from your face. But because they're both on the same side, it's also going to be cis. That's the same molecule. What would the trans look like? Will they be opposite? This one's coming at you, that one's going away from you. Going away from you, going at you. If I flip this over, I would get this. Make sense? So what is this one here? We got 1, 2, 3, 4, 5, 6. So it'd be hexane. So it's cyclic, so cyclohexane. And what's sticking out of it? That is 1, 2, 3 total, so it's propyl. Is it N-propyl or isopropyl? It's split on the end, so it's isopropyl. So is this. So it's di-isopropyl cyclohexane. And the numbering system would be 1, 2, 3, one possibility, or 1, 2, 3, 4. So the lowest numbering system is 1, 3. So what about this one? You can see it's cyclohexane. There's a methyl group and a 1, 2, 3, 4. So it's butyl. Which butyl is it? It's not split on the end. It's not as spherical as you can be, so it's not tertiary, but that's a secondary carbon right there. See that? It's bonded to 2 other carbons before it bonds to this rest of the molecule. So that's sec-butyl. So, which comes first? Well, this is always a point of contention, but butyl would come before methyl. Do we use the sec-butyl, the sec part, or we just use the butyl? Mostly we just use the butyl. So sec-butyl comes alphabetically before methyl. And then this is going to be 1, 2 or 1, 2. When I'm putting the numbering system, it's more logical to put 1, 2 than it is 2, 1, if you know what I mean. So then when we name alkyl halides, alkyl halides are not hydrocarbons, but we really treat them as such. And nobody seems to talk about it this way, but really what we're doing is we're telling people that no, the halide is not elevated to the status of being named as a functional group. So therefore we just name it as a substituent. But then when you get to organic chemistry textbooks, they often have a whole chapter on alkyl halides and substitution reactions. Anyway, so F is fluoro, chlorine is chloro, bromo, and iodo. And acetine basically is so rare we don't even use it for anything. So we have 6 in a row and it's cyclic, so cyclohexane. That's a chloro and a methyl. So chloro comes alphabetically before methyl. And the numbering system is 1, 2, 3, or 1, 2, 3, 4, 5. 1, 3 versus 1, 5, so I'll go with the 1, 3. Then it makes sense to put the 1 first, right? 1, 3 instead of 3, 1. You can see that these are opposite to each other, so it's trans. So this is simplified for us. We will use the systematic name that we just got through doing. We treating the halogen as just a substituent. But we have molecules like 2-bromopropane. The common way would be isopropyl bromide. So here they're actually naming it as if it was a functional group. But we, in IUPAC, modern IUPAC, we name it as a substituent. So I think this is a point of difficulty that needs to be straightened out. But anyway, for simple substituents, you use cyclo and iso and neo in alphabetical order, but you ignore di, tri, tetra, tert, and sec. Okay? And I'm not even sure I agree with that. I think tert butyl, sec butyl, I think they should be used up here, but because neo is, but they don't do that. And for complex substituents, you put the entire substituent in parentheses and use the whole name of the substituent to alphabetize. For example, looking at this, got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 carbons in a row. Obviously, it's going to be decane, right? So then I have, on this decane, I got 2 fluorines over there. And notice I got to use the lowest numbering system, right? So 1, 2, 3, 4, 5, 6 is going to be one way to do it. 1, 2, 3, 4, 5, 6 is the other way. So the same, it doesn't matter. So how do I name these 2 fluorines? I just say they're on carbon number 6 and there's 2 of them. Okay. But what about this one? So this whole thing is a substituent. It's on carbon number 5. And what is the substituent? It's difluoromethyl. It would be methyl, but the 2 hydrogens were replaced with fluorine, so difluoromethyl. See how we use the entire thing? But over here we don't. Anyway, so the physical properties of hydrocarbons, they only have nonpolar bonds. Okay. So what's the only attractive force possible? London's. Okay, what about the physical properties of alkyl halides? Well, I've always done this. It's hard to find a textbook to do this. I simply looked at the electronegativity values. And you can see that fluorine and carbon is a strongly polar bond capable of hydrogen bonding. Carbon and chlorine is a polar bond capable of dipolar attractions. With bromine, it's a weakly polar bond, so maybe capable of weak dipole attractions. And if you look at iodine, it's a nonpolar bond. It can only do London's. So if you have something like fluoromethane, that's probably going to be soluble in water. Fluorochlorine, probably soluble in water. Bromomethane, maybe kind of soluble in water, but not very. And iodomethane, probably not at all. So here's some information on WD-40. It's pretty interesting. So this guy, I don't know if he was the guy who they made that movie about. Oh, go ahead. They made a movie about, I don't know what they called it, Rocket Man or something like that. But I don't know. I don't know if he was the one who they came up with the idea about this guy. But yeah, so he was just trying to protect his rockets from rusting. So here's some halogenated compounds. We tried to not use them because they're persistent in the environment. Because when you put chlorines and stuff on things, bacteria have a hard time dealing with it. They don't all have the enzymes to break it down. So here's methane, chloromethane, dichloromethane, trichloromethane, tetrachloromethane. This would be nonpolar, polar, 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 and again, nonpolar. Okay. Because it's symmetrical. So these three were used in dry cleaning for a while. Now they replaced them with these right here because they're a little bit less harsh on the environment. Basically because there's oxidative reactions that help you break this double bond and you get into radicals that break down easier. Then the freons that are used in refrigeration are usually halogenated methanes and ethanes. And I won't go through the chemistry of this yet, or I won't anyway, because it's all free radical chemistry, but chlorofluorohydrocarbons take ozone and break it down into oxygen. So ozone is very important because it absorbs ultraviolet radiation. So if we didn't have ozone, we'd all be getting much more ultraviolet radiation and we'd have more skin cancer and everything. And there are places in the world right now where there are holes in the ozone layer, and it is dangerous to be exposed to the sunlight there. But it's over the arrow, it's a catalyst. So that means it's not just breaking one, one of these doesn't just take one of these and break it down. One of these can actually break down thousands, maybe even millions of ozone molecules before they finally get destroyed. So here's some of the refrigerants. There's R11, 22, 12, 134A. Here's their ozone depletion potential and global warming potential. Okay. So here's DDT. And my generation was quite concerned about DDT and a lot of chlorinated or halogenated pesticides and stuff like that, like chloridane, heptachlor. So here's DDT, dichloro, diphenyl, trichloroethane. So you can see it's dichloro, diphenyl, and then this right here is ethane, right? Carbon and a carbon. And there's 3 chlorines over there. That's where they get the trichloro from, right? Here's the ethane right here. By the way, I would never ask you to name something so complex. Okay. I remember when I was a kid, they used to spray DDT up into the valleys here in Hawaii, and we'd smell it. You'd come around at night and yeah, so there'd be a truck going through the neighborhoods and just spraying this stuff to kill mosquitoes. I remember back in maybe the mid 60s, we lived in Hawaii Kai in a new street that my dad had built. My dad was a contractor. And they went around putting this anti-termite stuff, which I think was chloridane, and they sprayed it in about a 1-2 foot path around the entire concrete slab. And then centipedes would come walking over and onto our carport area and get about 10 feet in and then just die. And it was that way the whole time we lived there, which had been about 20 years. So the lifetime of chloridane is really, really potent. So now chloridane is bad. But chloridane in the old days, you would put it in the soil, it would stay there, it didn't migrate away. Now all the new stuff they put in there is only good for about 5 years. So you got to do it every 5 years because it doesn't stick around. And this is simply an interesting molecule. They were trying to find an artificial blood to carry oxygen, and they found that this molecule could actually carry oxygen right here inside its cycle right there. And how they make this is you take cyclopropane and you take a chlorobutane or something like that, and then you do a substitution reaction and you connect it onto here somehow, and that's a very simple reaction. And then you treat it with fluorine gas, and every single hydrogen will be replaced by fluorine. You don't get partial replacement. They all go all at once. It's kind of interesting. So anyway, that was naming and physical properties and an introduction to some of the molecules. And so now we're going to look at the chemical properties. Like I said, we're going to give numbers, consecutive numbers to all of them. So the first one is combustion. And I gave two examples. One is with sufficient oxygen and one was with insufficient oxygen. So if you have sufficient oxygen, that carbon goes all the way to carbon dioxide. That hydrogen gets oxidized all the way to water. If you take a hydrocarbon and you burn it all the way, you get nothing but CO2 and water. And of course, it gives off heat because it's an exothermic reaction. Notice the stoichiometry. For every one of these, you need two of those. What if you don't have enough oxygen? Then you might get incomplete combustion and you might get some carbon monoxide. Notice that you get less energy, it's less efficient, and carbon monoxide is toxic because it combines with your hemoglobin and it's hard to get it off. So what about pentane? So if you had me for general chemistry, I give you guidelines to balance reactions. And so some of the guidelines are, you do elements like this. The very, very last thing you do is you do the element. When I put the 5 over here to change for carbon, I also change for oxygen. When I put the 8 over here to change for oxygen, I only change oxygen. And then another guideline is that you really should do hydrogen and oxygen last. Because chances are, if you do the other elements, hydrogen and oxygen become automatically balanced. Because they're just not very acrobatic. They can only do a certain number of things. So that means that you should concentrate on balancing the carbon first, then the hydrogen, and then last the oxygen. So 5 carbons, I had to put a 5 here. 12 hydrogens, I had to put a 6 over there. Now I add up all the oxygens over here. 10 over here, 6 more over here. So that's 16 on this side. So I need 16 on this side. There's 2 in each one, so 16 divided by 2 gives me 8. And now you can see it's balanced. What about for hexane? Okay, so 6 carbons, so I had to put a 6 here. Here I got 14, so I had to put a 7 over here, right? You get 14 hydrogens. Now to look at the oxygen, 12 oxygens plus 7 more is 19. So I need 19 oxygens over here, and there's 2 in each one, so that's 19 halves, or 8.5. But we know we cannot have half of an oxygen molecule. But now we have it balanced. This is the equal sign right here. So if I take this whole equation and multiply both sides by 2, then I can get rid of that half right there. See how that works? Okay. So maybe we can do one more. Aliphatic substitution. You're substituting the hydrogen with a halogen. Almost always we simply use chlorine and bromine. Fluorine is too hard to control, so we usually don't use it. So here's mono substitution. And oftentimes they will put UV light over the arrow because it's a catalyst. So all I'm going to do is take one of these hydrogens off and replace it with a chlorine. You notice how I switch this up? If you look at this molecule right here, every single hydrogen here is identical. So one of the hydrogens gets replaced with the chlorine. Now, what happens to the other chlorine and the hydrogen that I took off? Well, it forms a small molecule, forms hydrogen chloride. So you might be wondering, what is the reaction mechanism here? What does the UV light do? The role of the UV light is to break this bond right here. So here's what the UV does. It breaks the bonds. So in the presence of the UV light, it's not really the Cl2 that's pulling off the hydrogen. It's the chlorine radical that pulls off the hydrogen. So it's a free radical reaction, and we don't care about the reaction mechanism in this class. But what I really wanted to get to is the Pauli substitution. So now I have this in a container, I have that in a container, I shine light on it, and I start to have this, 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 and this in the container. So why could this not continue to react with this? Well, it can. So now, these hydrogens are not the same. You see that? Here they were the same, now they're not the same. So, these two hydrogens may be the same, these three hydrogens may be the same, but this and this are not the same. So now I have two possible substitution products. One would be if I substituted one of the hydrogens here, which would be this one. And one would be if I substitute one of the hydrogens over here, which would be this one. So the two possibilities are 1,1-dichloroethane and 1,2-dichloroethane. Okay. But I kind of wanted to get through this so you could see that, you know, you might have to stare at this for a few minutes. Make sure you understand that these two carbons are different, these two hydrogens are different than these three over here, because that carbon and that carbon are different from each other now. Anyway, so anybody have any questions before we take a break for a day?
When do you typically upload your YouTube recordings?
Right after. As soon as I shut this down, it starts to convert it. So Zoom has to do a conversion, and then I upload that to YouTube, and then YouTube has to do a conversion. And then they have to have somebody look at it or something like that. It's probably a robot that looks at it. So it takes probably an hour, sometimes more.
Right now, when I click on the YouTube link on La Lima, there aren't any videos like on your page yet. Is that the right way to do it?
No, go to the playlist. So I'm trying to protect your guys' identity. So what that means is that if I were to make this video public, anybody could find it. So what I've learned to do, and I think nobody knows this, I make the playlist public so you can find that, but all the videos in the playlist are unlisted. So you have to click on the playlist and then you'll find 341 Unit 1 or
Okay.
something like that.
Okay,
Yeah.
I see it now. I was looking under videos.
Yeah. So it's kind of being sneaky about it to protect you guys' identity. Okay, so any other questions?
When we were talking about the different electronegative levels between carbon and the different halogens, is there a certain number for the electronegativity difference that says whether or not it's nonpolar or not?
Yeah, if it's less than 0.5, we consider it nonpolar.
Less than 0.5. Okay.
5, yeah. Yeah, that's in that review of chapter 10.
Okay.
Anything else? Okay, you can always email me and use the forums, and I will see you guys tomorrow. Okay, take care now.
Thank you. Have a good day.
You too. See ya.